So the topic I'm going to present today is a functional perspective on the semiotic features of science animation. As Len mentioned, I come from a different background, so I'm not at the field of science education. I came from the background of linguistics and semiotics. So I draw upon a lot of concepts from linguistics and semiotics to model animation, and I focus mostly on the semiotic features of science animation. So firstly, I would like to have a bit of review of studies on science animation to this day. So a lot of studies focus in this field on the effectiveness of animated instructional materials for learning. And the majority of them use experiments to compare static images with animation and to see whether animation is superior in facilitate science learning. And besides focusing on the end result of whether animation is superior or not, they investigate the cognitive processes involved in processing dynamic visualization, as the presentations that we have already listened to in this morning. And interestingly, a lot of those studies come up with contradictory conclusions in terms of whether animation is superior in knowledge acquisition or not. And one problem that may partly explain the contradictory conclusions in this field of study is a problem of animation blindness, which is already pointed out by some science educators and science education researchers. Like what Bernie and Betrancott pointed out, the semiotic characteristics of the representations was largely overlooked in the multimedia literature so far. And also, like Plisner and Professor Lowe mentioned, the field of research on learning from animation still lacks a systematic and comprehensive characterization of educational animations that could provide a basis for guiding its future development. And to do justice to the work done in this field, we do have some science education researchers that examined the semiotic features of animation, represented by Professor Lowe's work. So Lowe mentioned in his work there are 3 types of animation, including form changes, position changes, and inclusion changes as 3 types of animation. Form changes, change of size, shape, color, and texture. Position changes refers to the movement of whole entities from one location to another, and inclusion changes referring to the appearance or disappearance of entities. And Lowe also mentioned both form change and position change can be highly perceptually salient when they contrast sufficiently with the context. Besides taking a micro perspective to look at the different types of changes, Plisner and Lowe also went on to offer a broader picture of a systematic characterization of expository animations. That is animation used to explain subject matter, and it's often used interchangeably with educational animation. So in their work, they proposed 4 dimensions that we can have a look at before we do those experiments to see which animation is better or whether animation is superior or not. The 4 dimensions include presentation, user control, scaffolding, and configuration of the animation under concern. And I'm going to focus on the part of presentation today. So for the dimension of presentation, it is concerned with the representations employed, whether iconic pictures, analytic pictures, or symbols or labels are used in the animation. And how does animation organize its information in terms of the spatial temporal arrangement and also the duration of animation. So this framework provides a very good basis for us to first take a look at what animations do we have, and then goes on to do those experiments to see their effect on science learning. But we still need much more in this field because we only have a very little amount of research on the semiotic features of animation. And this work as well as the presentations that I have been attending for this morning, seems to signaling a shift in the research focus in this field. We are shifting from whether animation facilitates learning or not to which animation facilitates learning and what kind of animation facilitates learning. Given the fact that animation has been increasingly popular in science education, it is of little value to still doubt whether animation facilitates learning or not. And it is more important for us to consider the semiotic features of animation and which animation facilitates learning and which animation suits what our target audience. So here, the question is, what do we semioticians have to offer? Because the topic is related to science education. It seems like I'm intruding into you guys' field. So what do we linguists and semioticians have to offer, have to contribute to your field? So as semioticians, our main tasks are to collect, document, and systematically catalog semiotic resources and to investigate how these resources are used in specific historical, cultural, and institutional contexts. Greatly influenced by Halliday's social semiotic view of language, we have been modeling semiotic resources other than language, and we have been developing various toolkits which can be adapted to capture the nuanced differences between different animation, which might create a difference in learning. So today I'm going to propose a functional perspective of animation. We have been listening to a lot of presentations focusing on cognitive processing of animation on the learner's side. So how about the animation itself? How about the semiotic features of animation? So I'm going to propose a functional perspective of learning from animation that might complement with the cognitive perspective that you guys take. Okay, so to draw an analogy with language, Halliday mentions language fulfills three broad functions: ideational, interpersonal, and textual. I would argue animation also fulfill those three different functions. And we can actually look at the animation by analyzing the three strands of meaning that animation fulfill. For ideational meaning, it is concerned with construing the experience of the world. So the two questions that we can ask when analyzing the ideational meaning of animation is, what experience are construed in animation, and how are those experiences construed in animation? And the interpersonal meaning has to do with the relationship between viewers and characters in the animation. It has to do with how does animation engage viewers. So that's another perspective. And for the textual one, it's concerned with information flow of animation. So how does animation organize its information flow? So the topic, the presentation today will, in this presentation, I will walk you through all those three strands of meaning fulfilled by animation. And before that, a bit of introduction of my data that I used. So I focused on science animation, for sure. And I collected a wide range of animation from online learning materials. So they are a bit longer animation than the one we have been watching in this morning. So the science animation is collected in my study from those three different channels. The course of Intro to Natural Sciences on the education website called study.com, and science projects on an online portal of an interactive whiteboard application called Explain Everything, and from TED Ed Animations. So those are all quite popular animations. And before going into our first dimension, into the ideational meaning of animation, I'm going to say a few things about the basic constituents of animation. So draw on Layout's study and Professor Lowe's study. There are two basic constituents of animation, elements and change. Elements are any visual entities that are animated, while change refers to the change that happens to the elements. Let's take a look at this animation.
Molecules are so small, you must use an indirect method to measure the kinetic energy of the molecules of a substance.
So in this short clip, we have as what Professor Low mentioned, a cluster of entity plus dynamics. So entity is here what I refer to as elements. We have elements as those little brown circles, and the change as the brown circles changing position. So we have basically two constituents of animation: changed elements, change plus elements. And for change, this is a framework adapted from Liao and Low. And this system network, this notation follows the tradition of systemic functional linguistics, which means a change can be either movement, transformation, illumination, or inclusion, or it can be either of the combination of the four. So we have the basic terms that we can use to describe animation: element and change. So first, for ideational meaning, as I mentioned, it has to do with construing experience of the world. And the two questions we can ask is what experience are construed in animation, and how are those experiences construed in animation? For the first question, what experience are construed in animation? Animation can construe single activity, like in this animation.
Consider a man walking in a zigzag pattern. If the man covers a total of 20 meters in the zigzag, then the change in distance is equal to 20 meters. Now let's say he takes 60 seconds to cover that 20-meter zigzag pattern. Therefore, the change in time is 60 seconds.
Of a man walking in a zigzag manner, and we can have more complicated activities. We can have a sequence of activities.
Since molecules are so small, you must use an indirect method to measure the kinetic energy of the molecules of a substance. As heat is added to a substance, the molecules move more rapidly. This increased motion causes a small increase in the volume, or amount of space, taken up by most materials.
So we have a series of activities connected through temporal order. We have the motion of molecules within an object. We have the heat added to the object, and then we have increased motion of the molecules, and then we have the expanding insides of the object. We have an activity sequence here. And we can also have animation construe single items, single entities, like in this one. Sorry.
Adhesives can be made from synthetic molecules or natural proteins and carbohydrates, like the vegetable starch dextrin, the milk protein casein, and the terpenes in tree resin.
So we have animation, the visual representation of animation construing single items of the vegetable, milk, and tree branch. And we can also have animation construing an item of classification. Like in this one, we have a classification of vertebrates classified into warm-blooded animal and cold-blooded animal. And by dragging those labels of the names of the animals, like fish, if we drag fish under cold-blooded animal, we construe an item of classification. We construe fish as a type of cold-blooded animal. And we can also have this animation construing item of composition. We can have all those bones. You can drag the bones, the animation. The bones can be animated to be displaced to this part, to the central part, to fit the human skeleton of hand.
Way you like. And the way this works is you can drag pieces from the right side and try to match them up where you think they should go as you start constructing this human hand. And then you can also move the labels around so that they go along with their appropriate position.
Those two are actually a bit different from the animations that we were watching, because those two are interactive animations, so students can do those operations by themselves to construe knowledge. So here, a summary is we have changes construe different experience. We can have animation, we can have changes construe single activity or activity sequences, and we can have changes construe a single item or item of composition or item of classification. And here, an important note to make is that for changes that construe activity or activity sequences, the change and the process of change are equally important. But for changes that only construe item, it's only the result of change that is important. We only want the item, or we only want the relations between the item. So it doesn't really matter about the dimensions of change, whether it's changed fast or slow, or which direction do the movement of the element follow. It doesn't really matter in terms of the knowledge, the target knowledge it construed. So it only functions to present elements or relate elements together. And the change itself have little meaning-making potential in construing field knowledge. If we go back to the previous video of adhesives, so the target knowledge is to show vegetable, milk, and tree branch as part of natural synthetic molecules. So the point is to just show these little things on the screen, and it doesn't matter how the animation shows it. So from this, it's an important note to make is the process of change doesn't really matter. So just make the animation simple, because it's not related to construing target knowledge. So we've already figured out the experiences construed in animation. And how are those experiences construed? It is concerned with how activities and items are depicted. And for a human character, we can animate it, we can depict it in this way, a very simple human figure. And we can also depict it in this way. Looks funny, right? With its body composed by geometric shapes. So we can have those two different depictions of human character with very different features. And here, the notion we can use to measure, to classify those two very different depictions is congruence. And congruence is a dimension that is concerned with how faithful the visual representation depicts reality. So whether it's congruent with reality or not congruent with reality. And the dimension of congruence is a line running from more congruent resembles reality, or less congruent, distancing from reality. Although this one is a very simple depiction of human, it's still placed on the scale as relatively more congruent with reality than the one on the left. And we can also, for non-human characters in our science subject, like we can have the structure of the atom depicted in a very schematic representation, or we can have it depicted in this way, as personified particles, electrons, protons, and neutrons, all with the human features of eyes, nose, and hands. And those are also two completely different styles of representation. And for this, we can introduce another dimension of essentialization that is concerned with whether the visual representation shows the essential parts relating to target knowledge, reducing unnecessary details, or whether it shows unessential details. The dimension of essentialization is also a line running from more essential with less details to less essential with more details. So we can also place the two representations of the atom structure on this line. We have the schematic one as a more essential one, only showing the structure and the particles within the atom, and also this one as less essential, with all those details and actually untrue details of the eyes, nose, and hand gesture and gestures. And if we take a look again at the video of adhesives, so we have the movement.
Adhesives can be made from synthetic molecules or natural proteins and carbohydrates, like the vegetable starch dextrin, the milk protein casein, and the terpenes in tree resin.
You can see the movement of all those vegetables, milk, and tree branches actually hop onto the frame, and the appearance of those things. And as we mentioned, this animation only functions to construe items instead of activities. So the change itself is not important. And we can say that the hopping movement is actually less essential to the target knowledge. And we can also classify this representation of introducing elements as less essential and which introduces more unnecessary details in relation to the building of target knowledge. So a summary for the ideational meaning of animation that we can examine is what experience are construed in animation, whether it's activity or item, and how are those experiences construed, that is, the different styles of animation, whether it's more congruent with reality or whether it's more essential towards the target knowledge. So we've mentioned we have some animation that include those unnecessary details in relation to target knowledge. So why, if they are unnecessary, why do some animators still do that? And we actually have a lot of animation that use those cute things. So that has to do with interpersonal meaning the animation construes. It has to do with the relationship between viewers and characters in the animation. And for this, the question we have at mind is how does animation engage viewers? And we mentioned different depiction styles when we are talking about ideational meaning. And those different depiction styles actually have different visual impact on viewers. It influences the relationship between viewers and characters in the animation. And it's actually found that a lot of science animation uses those cute little personified non-human character to add a sense of humor. And we can propose humor as another continuum that we can describe the representations in animation. That is the degree to which a depiction is considered as humorous. And it is found that characters which are less congruent with reality, as the ones we just saw about a very weird-looking person, and the personified particles of atoms, are less congruent with reality, but they actually elicit greater amusement from viewers. So if we have a cline of humor, we have the cline running from more humor, which elicits more amusement, engages the viewers more, to less humor and less amusement, less engagement with the viewers. And we can place all those representations that we just mentioned about incongruent with reality along the cline that is closer to the more humor, the more amusement end, and place. So this one is placed in terms of, is placed as lower of humor because it is still more congruent with reality. But you can imagine this one as still somehow engages viewers if you place a photo of the real human in your animation. And also, for the personified non-human character, it's considered as more humor in terms of the representation compared with the schematic representation of the structure of atom. So as a summary for interpersonal meaning, by examining the depiction styles of characters in animation, we can understand the overall ambience of different animations, whether it has more playfully humorous elements, whether it's orienting more towards serious science, or whether it's orienting more towards popular science by engaging the viewers more. So the final aspect of the 3 strands of meaning that I'm going to introduce is textual meaning of animation. Textual meaning has to do with the information flow of animation. And the question we can ask is, how does animation organize information flow? And this is actually related to one of the 4 dimensions proposed by Pleasant and Low. That is the one of spatial temporal arrangement under the dimension of presentation. Animation has a spatial and temporal dimension. We can examine the animation to see whether the layout of animation, whether animation makes use of both of the 2 dimensions, both spatial or temporal, or whether it privileges each or either of the 2 dimensions. So we can classify the information structure of an animation as either retain or replace. We can have
Each of these physical feats is made possible by a fish's form, which in most species is a smooth, elongated body, fins, and a tail.
So we have one element added on top of another within one space. And we can also have one replacing another, like this one.
These features are shared across thousands of fish species, each introducing its own variation.
So for both of the animation, we have appearing of elements, but they follow different information structure. The first one, we have one element appearing on top of another, with the previous one still stayed on the screen. But for the second one, we have one element replaced by another, so we have a successive replacement of elements in animation. And if we look at the retain one, we can further classify it into decomposed and cumulative. So for decomposed one, it's often used to walk viewers through complex diagrams like this one.
As heat is applied to liquid water, the molecules move faster and the temperature again increases. During the phase change from liquid to gas, the added heat is stored in the molecules as, once again, potential energy, and the temperature remains constant. The added heat is used to overcome the remaining forces that hold the molecules together within the liquid. This allows the molecules to move even further apart and form a gas. Once again, the heated energy during the phase change is stored as potential energy.
So here we have, at first, an overall picture of the complex diagram, and then we have what's Low called as scaffolding to decompose the larger picture into smaller chunks of information units, which also functions to relate segments of voiceover to parts of the image to direct viewers' attention. And we can also have a retain cumulative, like the one we mentioned about the composition of fish. So a summary of the different information units utilized by animation is that we have 2 broad types of information structure, retain and replace. And for the retain one, it actually makes use of both the temporal and spatial dimension of animation, while the replace one privileges the temporal dimension. And by making different use of the 2 dimensionalities of animation, different information structure have different potentials to construe science knowledge. For the retain one, it allows viewers to make a connection between the elements because they are placed within one space. You don't need to refer back to the video to make a connection to the elements. And is often used to construe knowledge like composition, classification, or comparison. While another note to make about the replace one is, as you can see, each element actually stays for a relatively short period of time. So it actually increases the information load placed to the viewers. In the last part of this presentation, I'm going to show you a case analysis to compare 2 videos on the same topic to give you a sense of how those 3 strands of meaning can be integrated to analyze animations. So I have two videos on the same topic of static electricity. One is from study.com and another from TED-Ed. I guess you are quite familiar with TED-Ed, so a bit of introduction about study.com. It is an American education website, and it is mentioned in this website that by enrolling in one of its lesson series, you can transfer college credits. So the target audience is presumably junior college students or senior high school students. Now, I'm going to show you part of the video to give you a general sense of how those two videos differ.
You probably know what happens if you rub a balloon against your hair. When you take the balloon away, some of your hair stands straight up, as if it's trying to follow the balloon. You may even know that it's caused by something called static electricity. But do you know what static electricity is, or why it makes your hair become attracted to the balloon? To answer these questions, we have to start with the atom. Everything in the universe is made of atoms, and every atom contains three types of particles called protons, neutrons, and electrons. The protons and neutrons are packed together in the nucleus at the center of the atom, while the electrons zip around the outside in a constant motion. For our discussion on electricity, we only need to concern ourselves with protons and electrons because they have a property called electric charge. The electric charge that electrons and protons possess is responsible for the form of energy that we commonly call electricity. Protons have a positive charge, which is easy to remember because the word proton and positive both start with the letter P. Electrons, on the other hand, have a negative charge, which is equal but opposite to the charge on a proton. If you bring one electron and one proton together, their charges cancel each other out, and we say that together they have no net charge. In most atoms, there are equal numbers of protons and electrons, so the atom itself has no net charge. However, there are many atoms that either give away electrons or accept electrons with relative ease. When this happens, we call the atom an ion. If an electron goes away, then the atom is left with more protons than electrons, and the atom becomes a positive ion. Likewise, if an electron comes along and joins the atom, then there will be more electrons than there are protons, and the atom will become a negative ion. The transfer of electrons from one atom to another happens all the time. Remember rubbing a balloon on your hair? This is a great example of transferring electrons, but why does it happen? The answer is your hair contains atoms that are happy to give away some of their electrons. On the other hand, the balloon contains atoms that want to accept those electrons and hold on to them. Therefore, when you rub the two together, a bunch of electrons transferred from your hair onto the balloon. As a result of this transfer, your hair became positively charged because its atoms were left with more protons than electrons, and the balloon became negatively charged because its atoms had more electrons than protons.
It can strike without warning, at any moment. You may be walking across a soft carpet and reaching for the doorknob when suddenly, zap! To understand static electricity, we first need to know a bit about the nature of matter. All matter is made up of atoms that consist of three types of smaller particles: negatively charged electrons, positively charged protons, and neutral neutrons. Normally, the electrons and protons in an atom balance out, which is why most matter you come across is electrically neutral. But electrons are tiny and almost insignificant in mass, and rubbing or friction can give loosely bound electrons enough energy to leave their atoms and attach to others, migrating between different surfaces. When this happens, the first object is left with more protons than electrons and becomes positively charged, while the one with more electrons accumulates a negative charge. This situation is called a charge imbalance, or net charge separation. But nature tends towards balance. So, when one of these newly charged bodies comes into contact with another material, the mobile electrons will take the first chance they get to go where they're most needed, either jumping off the negatively charged object or jumping onto the positively charged one, in an attempt to restore the neutral charge equilibrium. And this quick movement of electrons, called static discharge, is what we recognize as that sudden spark.
Okay, so we can see those are two animations with very different styles, right? And I'm going to segment those two videos into shorter clips in terms of the target knowledge it construes. So one of the very important target knowledge for those two videos is the composition of atom. Every atom contains three types of particles called protons, neutrons, and electrons. Protons are positively charged and electrons are negatively charged. Normally, the electrons and protons in an atom balance out. So let's take a look at how study.com construes this part of knowledge.
But do you know what static electricity is, or why it makes your hair become attracted to the balloon? To answer these questions, we have to start with the atom. Everything in the universe is made of atoms, and every atom contains three types of particles called protons, neutrons, and electrons. The protons and neutrons are packed together in the nucleus at the center of the atom, while the electrons zip around the outside in a constant motion. For our discussion on electricity, we only need to concern ourselves with protons and electrons because they have a property called electric charge. The electric charge that electrons and protons possess is responsible for the form of energy that we commonly call electricity. Protons have a positive charge, which is easy to remember because the word proton and positive both start with the letter P. Electrons, on the other hand, have a negative charge, which is equal but opposite to the charge on a proton. If you bring one electron and one proton together, their charges cancel each other out, and we say that together they have no net charge. In most atoms, there are equal numbers of protons and electrons, so the atom itself has no net charge.
Nature of matter. All matter is made up of atoms that consist of three types of smaller particles: negatively charged electrons, positively charged protons, and neutral neutrons. Normally, the electrons and protons in an atom balance out.
Okay, if we first take a look at the ideational meaning, we can see both videos construe the composition of atom and the properties of the particles within the atom. But I fully agree with what Professor Low mentioned about in order to understand the affordance of animation, we need to tease apart animation and voiceover to see what animation does and what voiceover does. So we can actually see here animation and voiceover has different weight in construing field knowledge in the two lesson videos. For study.com, both animation and voiceover shows the composition, but it's only the voiceover that mentions the movement of the electrons. The animation doesn't show the electrons zipping around on the outside in the constant motion, but the voiceover mentions it. But for the TED Act 1, if you still remember, it's only the voiceover mentions the composition, and the animation only vaguely shows the composition in the last frame, in the last few seconds of the video. And it's not quite clear about what those symbols stands for because they are introduced in that way. So it's not very clear which atom, which particle is which one for students without any prior knowledge. And also, the movement of electron is indeed shown to be constantly moving and zipping outside in the atom, but it's not mentioned in the voiceover. So for students may not even know that electrons are moving, and how would they know those symbols stands for electrons? So here, for TED Ed, voiceover plays a more important part in construing field knowledge, but animation only vaguely shows it and does it in a very unclear way. For the depiction styles of study.com and TED Ed, the composition of atom is reduced to a schematic representation with circles standing for particles, minus as negative and plus as positive. But for TED-AD1, those particles are personified and with facial expression and gesture reinforcing their electric charge. So if we measure that in terms of the two dimensions of congruence and essentialization, we can see this representation of the atom structure is higher in terms of congruence and higher in terms of essentialization relation to target knowledge. But for this one, it's lower in congruence and lower in essentialization. And the reason, and relating to the construing of composition, the information flow plays a very important role. So for textual meaning, the two animations actually use different information structure to construe composition. For the study.com one, it first identifies protons and electrons in this way, and later in the structure, and then later when it shows the structure of the atom, it goes like, in an atom, there are equal numbers of protons, and the protons changing color, and equal numbers of neutrons, and equal numbers of electrons, and electrons changing color. So here, the animation helps viewers to identify which particles are which by achieving a synchrony between animation and voiceover. If you want to have a look at that.
Protons have a positive charge, which is easy to remember because the word proton and positive both start with the letter P. Electrons, on the other hand, have a negative charge, which is equal but opposite to the charge on a proton. If you bring one electron and one proton together, their charges cancel each other out, and we say that together they have no net charge. In most atoms, there are equal numbers of protons and electrons, so the atom itself has no net charge.
So we can see here, this animation uses the information structure of retain decompose. It first shows an overall picture and decomposes it into smaller information units to reinforce which particle is which one. But for TED-AD, at first it shows everything is contained with atom, and it shows this representation of atom as a personified human figure. And then it decomposes atom into the three particles, but without showing the atom and the particles together. And after that, it shows the movement of the particles within the atom without clearly identifying which particles are which one. And we can see here, the animation uses the information structure of replace. So it's one representation replacing the previous one by showing the atom, the composition of the atom, and the movement of the particles in three separate frames, which is not very conducive for the viewers to build a holistic picture of how the structure of atom looks like. And in terms of the interpersonal one, we can see very funny representations with human figures depicting as not so human and non-human characters personified. And we can see here the characters, both human and non-human, are depicted in a humorous way in TED-AD, which elicits greater amusement from viewers and encourage deeper engagement, which gives the animation a sense of cuteness and humor and humorous. So another target knowledge for this lesson video is the transfer of electrons. There are many atoms that either give away electrons or accept more electrons with relative ease. And for study.com, it shows I guess I'm going to play you the video again.
The transfer of electrons from one atom to another happens all the time. Remember rubbing a balloon on your hair? This is a great example of transferring electrons, but why does it happen? The answer is your hair contains atoms that are happy to give away some of their electrons. On the other hand, the balloon contains atoms that want to accept those electrons and hold on to them. Therefore, when you rub the two together, a bunch of electrons transferred from your hair onto the balloon. As a result of this transfer, your hair became positively charged because its atoms were left with more protons than electrons, and the balloon became negatively charged because its atoms had more electrons than protons.
But electrons are tiny and almost insignificant in mass, and rubbing or friction can give loosely bound electrons enough energy to leave their atoms and attach to others, migrating between different surfaces. When this happens, the first object is left with more protons than electrons and becomes positively charged, while the one with more electrons accumulates a negative charge. This situation is called a charge imbalance, or net charge separation.
So here for study.com, we have that movement, the transfer of electrons, as repeatedly show single electron displacing. So it's just a simple and slow movement. It's just one electron displacing at a time. But for TAD-AD, we see multiple electrons displacing by hopping out of the frame. So it's not simply the particles displaced from one place to another. It's the particles hopping out. So it has more complex and quick movement. And as we mentioned, the decline of essentialization, here for the target knowledge, what we really want is just electrons changing place from one place to another. On the study.com, the movement represented in study.com is considered as higher in terms of essentialization. But for TAD-AD, it's considered as less essentialization. It has all the unnecessary movements of hopping, but it works to personify the particles and adds humor to it. And actually, TAD-AD, I had a look at the TAD-AD animation and found there are actually a lot of gratuitous changes in the animation with all those unnecessary details that is not so relevant to the target knowledge, as we can see here.
In certain conditions, charge separation will occur in clouds. We don't know exactly how this happens. It may have to do with the circulation of water droplets and ice particles within them. Regardless, the charge imbalance is neutralized by being released towards another body, such as a building, the Earth, or another cloud in a giant spark that we know as lightning.
Moving of the clouds is also depicted as the clouds expanding and contracting while displacing, but the target knowledge is just to show the cloud as changing its property. So in summary, the TAD-AD animation fails to construe the composition of atom, partly due to its organization of information. It's organized in different space, within different space. And the visual representations in the TAD-AD one strays away from reality, but this incongruence with reality adds a sense of humor and cuteness to the serious science stuff. And in terms of essentialization, the TAD-AD animation is featured with less essential changes which do not function to construe the target knowledge, but it's more interpersonally engaging. So it might be said that the TAD-AD animation is more suitable for younger children to watch. So a general summary of this presentation is by proposing a functional perspective of animation, we can analyze different strands of meaning in animation. For ideational, we can examine what experiences are construed in the animation, and we can have a look at how are those experiences construed in the animation in terms of the two dimensions of congruence, whether it's congruent with reality or whether it's essentialized in terms of the target knowledge it tries to build. And interpersonally, how does the animation engage viewers in terms of the decline of humor? And for textual, how does the animation organize information flow? Does it follows a structure of retain or replace? So the take-home message for this presentation is, by introducing a functional perspective of animation, we can tease apart different meaning-making potentials of animation. And a very important note to note is that interpersonally engaging doesn't equate with ideationally conducive to knowledge building, as we have as the videos that I just showed you today. And also, from a semiotician's perspective, the best I can do so far is to articulate the nuanced differences between different animations, which has two implications for our researchers and science educators. For researchers, both semioticians and science education researchers, that is to provide a basis for further examination of these differences on viewers' perception and on knowledge building, especially for those invisible experiences like the animation of force. Whether we animate it by using a simple arrow or we animate it by personifying it as a human figure, does that have any difference in terms of the viewer's perception and building of knowledge? So this is a problem that we may consider in the future, and for science educators to provide different lenses to select educational animation targeting different learners. Okay, so this is my presentation. Thank you very much.